again, back with more science, section 1, and today we're going to talk about the electromagnetic spectrum. So, just as a reminder, the length of a wave, right, corresponds to kind of how big it is, right, and the bigger it is, its frequency is lower, right. The frequency being basically the speed of the wave, kind of over a certain amount of time, right. If we kind of go back up here, right, the period is the amount of time that elapses between oscillations, right. The frequency is the number of oscillations in a given amount of time, right. And so when we have bigger wavelengths, we have lower frequency radiation, right. And that is the electromagnetic spectrum, which is the continuum of electromagnetic waves. And if I can actually pull up here, right, so again, just to kind of look at these, if we create a wave here, right, if we have a big wave such as this, right, and then we look at the wavelength, right, which I guess I would need to maybe do something more like that, right, we're going to see that from one point to another, right, that is going to determine the wavelength, right. So again, the larger the wavelength, the shorter the frequency, right. Okay. My beautiful art there. So again, lower frequency, which also corresponds to a higher wavelength on our line graph here. Then over here, we have a higher frequency with a lower wavelength. And we're going to start with radio waves. And this might not all be to scale. This graph I'm making, I'm kind of just making it as we go, right? So this radio waves are greater than or equal to 30 centimeters in length, right? So that means they're quite large, right? Oops, nope, that's not what I want. I want that. Okay. They are the longest wavelengths of the electromagnetic spectrum, again, 30 centimeters or longer, and we even have some AM radio wavelengths that go as long as 1 kilometer, right? And a lot of the things that radio waves are used for: radio and television communications, and then radar, satellites, and walkie-talkies. Okay. Next up is microwaves, and microwaves are between, 1 micrometer, 1 millimeter. So next up we have microwaves, which is between 30 centimeters to 1 millimeter. I want to make sure I'm getting that right before I keep posting that here. Yeah, 1 millimeter and 30 centimeters. They're using microwave ovens, of course. Then they're also used in aircraft navigation and radar, and then general scientific research, which we will be getting into more, especially astronomical research, of course, especially with things like the cosmic microwave background. Next up, we have infrared waves, which are between 700 nanometers to 1 millimeter. Okay. So next up, we have infrared, which is between 1 millimeter and 70 nanometers, 700 nanometers, and 700 nanometers. Okay. In infra, right, means below, right? So it's the spectrum that is below red, right? It's the part of the spectrum that is below red. Infrared waves play a really important role in our world. They are absorbed and emitted by most materials. And when material absorbs infrared waves, it increases the kinetic energy of atoms and molecules, basically just making them move around a lot more, right? Causing them to vibrate, essentially, which causes them to get hotter. The applications for infrared waves include meteorology, night vision devices, communication, and astronomy. Again, we'll go into its astronomical uses in a little bit, or in a later video, I should say. Okay, so then we have higher frequency radiation, right? Our 3 sets of high frequency radiation. But we're missing something right here in the middle, which we'll come back to here in a little bit. But our high frequency radiation starts with ultraviolet light, which is, again, ultra, right, kind of means above violet, right, above violet, right? And this goes from, was it 400 nanometers? Yes, 400 nanometers to 10 nanometers. X, and then 10 nanometers, which then means that whatever this is about 700 nanometers to about 400 nanometers in length, right? The sun is a major source of UV light on Earth. We do have most of the sun's UV light absorbed by the atmosphere. And UV light itself is quite harmful to humans. Basically, anything below 400 nanometers is going to be pretty harmful. It has practical uses in sterilization of medical instruments and what is called silicon lithography, which is what is used to produce computer chips. It's also important in scientific studies, which, they're being very vague on that, but here we are. And then air and water disinfection against viruses and bacteria. Okay. Next up, we have X-rays. And X-rays go from 10 nanometers to 10 to the negative fourth nanometers. Oops. 10 to the negative fourth nanometers, right? So what is that? 100, was that 1/100,000th of a meter or something like that, of a nanometer or something like that? I shouldn't be saying things. You're familiar with X-rays because they are used in the examination of bones, teeth, and organs. But they are also, again, very energetic. They can be very harmful to living tissue, which is why when you do go in for X-rays, you usually wear a shield to protect your body, the parts that they don't want hit by the X-rays, right? And then lastly, shortly not leastly, is gamma rays. Right, and gamma rays go from 10 to the negative fourth nanometers to 10 to the negative 10 nanometers. Oops, that doesn't look like anything. 10 to the negative 10 nanometers. They are very short wavelengths, obviously, and they're highly penetrating, right? They are mostly emitted by nuclear transitions, and they're extremely, extremely dangerous to living tissue. And if it gets absorbed, it could be game over for you, right? At the same time, though, the destructive capability has been harnessed, for example, destroying cancerous tumors. So they do have their benefit, right? But they're very dangerous. Now, this classification system does not mean that there is literally anything. They're different, like in terms of the composition of these waves. The only thing different is the frequency and wavelength, right? That is the only thing that separates them, right? It's not like here's these box of blue X-rays and these box of green gamma rays, right? It's they are the categories, right? The kind of cutoff lines of each category is very hazy, right? Because it's not really categories. It's just classifying these different speeds of wavelength, right? Of frequency, right? They're all a manifestation of the electromagnetic wave phenomenon, right? Again, the only thing they differ in the frequency of oscillation, and there's no sharp boundary. Okay, now let's get into that middle section that we didn't get into yet, which is the visible spectrum, right? So right here we have visible light. Okay, and so it is all these set of wavelengths detectable by the human eye, and it goes from violet to red, with violet being up here at 400 nanometers, and then red down here is 700 nanometers. So the highest wavelength of light is red. The lowest frequency of wavelength of light is red, right? Whereas the highest frequency is violet, and the lowest wavelength is violet. Okay, so I could totally see them asking a question to try to trip you up on something like that. Human eyes are not equally sensitive to all wavelengths. Peak of sensitivity is around 560 nanometers, which is yellow-green light, which is probably more of an evolutionary thing, which we'll get into here in a little bit, but it's most likely an evolutionary thing for two reasons. Number one, of course, yellow is kind of the way we sense most of the light from the sun, but then also green is the light of plants and many animals, right? Which means that evolutionarily speaking, it would have been best for us to be able to observe green objects very well. And then, of course, we have our visible lights. Roy G. Biv, right? We got red, orange, yellow, green, blue. I'm not going to make it. Indigo, and violet. Indigo kind of just being like a deeper violet, I guess. Yellow-green, again, right here, 560 nanometers. That's where we're kind of looking in terms of what we see well, which, you know, probably is pretty, it's pretty close to halfway through the spectrum, right? There are an infinite number of frequencies, of course. That's how numbers work, right? So, like, you know, you could have red-orange to, you know, red-orange or red-orange-orange or, you know, stuff like that. Okay. Now, light made up of all colors in the visible spectrum do appear white. In fact, the light from the sun is considered white light. Again, I said it looks yellow, right? But it gets considered white light. In the late 1660s, our boy Isaac Newton demonstrated the composite nature of white light using a prism to separate the sunlight to a spectrum of colors, right? And then using a second prism to then reconstitute those colors into white light. The sun emits almost all over the electromagnetic wave frequency chart, but 99% of it belongs to the UV, visible, and IR portions of the light. And the peak of the solar intensity is right in the visible spectrum, again, at that kind of yellow-green area. And again, they say a lot of evolutionary processes have caused humans to be most sensitive to the light most frequently emitted by the sun. Right? So maybe if the sun was more likely, or its peak of visible its peak of solar intensity was in the UV light, maybe we'd be more able to see UV light. Some animals and insects, in fact, are sensitive to UV and IR portions of the spectrum. Bees, for example, are sensitive to ultraviolet light because it directs them to pollination sites on certain flowers. Okay, and that's going to do it for the electromagnetic spectrum. Again, we have radio waves, microwaves, infrared, visible light, G-BIV, ultraviolet light, X-rays, and then gamma rays, right? So that is the spectrum. And this spectrum is going to do a lot for us because it's going to allow us to really do some amazing stuff when it comes to astronomical observation, understanding how the spectrum works, and stuff like that. But that's for another video. And until the next video when we go over thermal radiation, thank you guys so much for watching, and I will see you in the next one.